Beta or hairpin match for amateur radio antennas. How common are they? They are exceptionally common. In fact, if you look at modern commercially manufactured HF Yagi antennas, the beta or hairpin match is arguably the industry standard. For homebrewers building directional arrays like Yagis, it is often preferred over gamma match because of its sheer mechanical simplicity and long-term reliability. How the hairpin match works. When parasitic elements, reflectors and directors, are brought close to a driven element, they drop the feed point impedance significantly, often down to 20 or 25 ohms. Feeding this directly with 50 ohm coax results in a poor SWR. The hairpin match solves this by acting as a mechanical L network. The series capacitor, the driven element, is intentionally cut slightly shorter than its natural half-wave resonant length. This makes the element naturally capacitive at the operative frequency. Shunt inductor. The hairpin is a shorted length of parallel transmission line attached directly across the feed point. Electrically, this acts as an inductor, so there are no separate high voltage capacitors or inductors. Together, the inductive reactance of the hairpin cancels the capacitive reactance of the shortened element, simultaneously transforming the low 20 to 25 ohm resistive impedance up to a perfect 50 ohms. Why it dominates HF designs? There are several reasons this design is so heavily favored, especially for outdoor HF arrays. No fragile capacitors. Unlike a gamma or omega match, there are no variable capacitors to weatherproof, seal or replace when they fail. It is purely mechanical tubing or heavy gauge wire. Effortless QRO. Because there are no dielectric components or tiny air gaps to break down, a hairpin match will effortlessly handle whatever a linear amplifier throws at it without arcing. Inherent balance. The driven element remains electrically balanced, split at the center, maintaining a cleaner radiation pattern. But there are also trade-offs. Boom isolation. The driven element must be electrically insulated from the boom using fiberglass or Derlin brackets. A gamma match, by contrast, allows the center of the driven element to be bolted directly to the grounded boom. Balance required. Because the feed point is balanced, feeding it with unbalanced coaxial cable requires a high quality 1:1 current balance right at the feed point to prevent common mode currents from traveling down the coax shield. Tuning friction. Adjusting the match requires physically sliding the shorting bar on the hairpin and adjusting the element tip lengths simultaneously, which can be an iterative and tedious process during the initial alignment. Tuning a hairpin or beta match is an iterative process because the hairpin's inductance and the driven element's capacitance interact. You cannot adjust one without slightly affecting the other. It is a balancing act, but with a modern antenna analyzer like a Nano VNA or a rig expert, you can visualize exactly what is happening in real time. Prerequisites. An antenna analyzer capable of displaying complex impedance R plus minus JX and SWR. Nano VNA is a cheap equipment which can do that. The antenna in the clear. The Yagi should be mounted at least a half wavelength above ground if possible, pointing straight up to minimize ground interaction or at least clear of surrounding metal structures. That is often a little difficult. A 1:1 current balance connected directly at the feed point. You will connect your analyzer to the input of this balance. The initial setup. Before making any measurements, you must start from the right physical baseline. Shorten the driven element. The hairpin match requires the driven element to be capacitive. Set the length of the driven element halves to be about 2% to 5% shorter than a standard resonant half-wave dipole for your target frequency. Set the shorting bar. Place the shorting bar roughly in the middle of the hairpin tubes. Ensure the connections are physically tight so you don't get erratic readings. Reading the complex impedance. Connect your analyzer and sweep across your target band. Ignore the SWR curve for a moment and look at the complex impedance R plus minus JX. You are looking for two specific numbers at your target operating frequency. R, the resistance. Your goal is 50 ohms. X, reactance. Your goal is 0, that is perfect resonance. Adjust the impedance, the R value. The position of the shorting bar primarily dictates the resistance R. It acts as an impedance transformer. If R is less than 50 ohms, move the shorting bar further outward away from the boom to increase the size of the hairpin loop. This increases the inductance. If R is greater than 50 ohms, move the shorting bar further inward closer to the boom to decrease the size of the hairpin loop. Move the bar in small increments, quarter inch or a few millimeters at a time, and recheck. I'll show an interactive computer generated demo at the end. Adjust the resonance, the X value. Once your R value is sitting nicely around 50 ohms, look at your reactance X and your resonant frequency, the point where X crosses 0. If the frequency of lowest SWR is too low, or if X is positive, inductive at your target frequency, the driven element is too long. Shorten both element tips equally. If the frequency of the lowest SWR is too high, or if X is negative capacitive at your target frequency, the driven element is too short. Lengthen both element tips equally. Most people use telescopic tubes if they are using aluminum tubes or other tubes for the element, that is the driven element. Additional smaller telescopic tubes are used for making this adjustment, which can go in or out, and finally after the final adjustment it can be clamped in position to avoid further movements. The iterative dance. Changing the element length in step 4 will slightly alter the R value you dialed in during step 3. Recheck the R value at your new resonant frequency. If R has drifted away from 50, tweak the shorting bar again. If tweaking the shorting bar shifted your frequency, tweak the element tips again. Repeat this dance until you have an SWR curve that is flat and centered precisely where you want it in the band. Once locked in, physically tighten all clamps and apply anti-seize or weatherproofing as needed. Anti-seize is a specialized lubricant paste applied to thread-end fasteners like bolts, screws and clamps to prevent them from locking together permanently. It is designed to withstand high heat, heavy loads and corrosive environments. Here is an interactive demo of what happens if you change the hairpin position and driven element length. Now this is perfectly tuned. You can see the SWR curve fixed at 14.15 megahertz. That's a 20 meter antenna. And when I move this hairpin position, see, and the hairpin position is moved. Now it is 67 here. You can see impedance 60 plus J0 and SWR has increased. If you move further, it is going to increase like that. SWR has increased. When the hairpin is moved, the SWR increases because the impedance increases. I'll come back to now it's 50 again, 1:1 SWR, and now I'll try changing this driven element. If you move this way, the frequency increases. That is, resonant frequency has gone near 14.200 megahertz. Impedance remains same, but the J value changes. You can see reactive component changes, negative. That moves like this. Resonant frequency has shifted to the end of the band. If you move it the other way around, that is, you are changing the length of the element, driven element. So along with that, there is change in resonant point. So when the resonant point is at 14, naturally at the center frequency the SWR is high. That is expected. So depending on, if you keep it like that, it's good for CW portion. But then the impedance, reactance, everything is different. So this is just an interactive demo to show that when you change the driven element length and hairpin position, there is changes in SWR as well as impedance, both the R value and the you can see now impedance increased, J value is different. So the curve position also changed. So this is how it happens when you change the length of the driven element and the hairpin position. Driven element length can be ideally changed using telescopic pieces of elements. Otherwise it is very difficult to cut and join